Good afternoon, ladies and gentlemen in Taiwan and all around the world. So I will be talking about the moon, but we are people living on Earth, and it is useful always to keep in mind differences. Earth is 6,000 kilometers, mean radius. The moon is 1,700. Mean density of Earth is 5.5. Mean density of the moon is 3.3. It says again something about surface gravity, 980 meter per square seconds, and 6 times smaller on the moon. And also look, oceans, 71% of surface area of Earth, and no free water on the surface of the moon. System Earth and the moon. This system rotates, it goes around the sun at the distance of about 150 million kilometers. Meanwhile, this is Earth, and around Earth, moon goes around for about 27 days on the mean distance, 384,000 kilometers. Historically, the moon was first considered as related to gods because objects in the sky is Greek goddess Selene, Chinese Chang'e, and then it was studied by scientists in medieval time like Galileo Galilei, and in 20th century, already geologists started to study the moon. So first was pre-telescope study, objects in the sky, then telescopic observations, Galileo Galilei, and later major relations of different formations on the moon surface were established before the space era, just analyzing the telescopic observations. The resolution of the best telescopic images were close 1 to 2 kilometers. Space flights on the moon started with Luna 1, long time ago, 1958, and the latest is Chang'e 5. They provided close observations, landing and in situ studies, samples delivered to Earth. Space flights on the moon, landing. It's problem of landing. We did not know to land, and we might sink in the dust. It was obvious there is dust on the surface, but this dust is just dust, very friable dust, and you can just sink and that's all over, or you can stand on this. And it was some struggle of opinions, and it is finished with landing of Luna 9, which first survived landing and sent panoramas, and we could see there some features and some rocks. And similar was a little later returned by Surveyor 1 of the US spacecraft. There were very useful lunar orbiter 1, 2, 3, 4, 5, which provided a lot of good high resolution images from the orbit. And we, not only Americans, but other nations used these images, including us, that time Soviets. We used these images to select landing sites for our manned expedition to the moon, which never happened, but we were working on it. So Apollo expeditions to the moon since 1968 to 1972, they were very successful. There was only one failure. It is Apollo 13. So you may believe or not believe in bad numbers. 13 was bad. But they survived this, returned safely to Earth. But they brought a lot of samples, put some instruments on the surface, and made a lot of photography from the orbit and on the surface. Soviet flights to the moon. Most successful were Lunokhod and landers for Lunas-Lunokhod, which brought Lunokhods, which provided some measurements, a lot of images, and 3 Lunas brought samples from lunar surface. You can see to the lower right, it is Luna 20 capsule with samples. Later you will may compare it with Chinese lunar sample capsule. So flights to the moon in the Cold War time. We in the USSR made attempt 48 times. Success was only 21 times, less than half, but we were pressing on. And the United States, they have approximately the same success and with much better, would say, successful percentage. So this is, you see above is Apollos, and when it is field circle, it is success. When it is circle, not field, it is failure. You see that we have, especially in the beginning, we have a lot of failures, but then success, failure, and so on. So later on came Clementine, which provided with good images of the lunar surface. It was lunar prospector who showed that in lunar poles there is some hydrogen. Probably it is due to concentration of water ice there. Then Japanese Kaguya, a lot of good images and other measurements. And Chandrayaan-1, Indian spacecraft, on board of it was American instrument Moon Mineralogy Mapper, which in particular showed presence on the surface of the moon some little layer, less than a few microns of water. You see this, it is where it is bluish, it is some water. It's on the surface of regolith particles. And then you see very recent missions, GRAIL, Gravity Recovery and Interior Laboratory, and of course, great success, especially important for us geologists, Lunar Reconnaissance Orbiter, which showed, provided complete coverage of the moon with images with resolution of 100 meters and 0.5 to 1 meter, significant part of the moon, resolution, significant part of the moon. You can see landers and traces of footprints of astronauts and rovers and so on. Then very recent Chang'e 3, and it is Mare Imbrium. And then on the back side of the moon in von Karman crater, rover Chang'e 4. And finally, it is very recent Chang'e 5 sample return from the Runker Peak. You see on the lower right, capsula. It's big capsula. It is interesting what is inside. I know that, I don't know, is it open or not? The rumors is that there is, and this is why the Lunar and Planetary Science Conference deadline was moved by 1 week later to January 12 to allow Chinese to provide some results, but just rumors. So what about us, Russians? We have close plans. Lunar Globe lander in this year, end of the year. It's just demonstration to land, to make some measurements, including to measure this presence of hydrogen, water, ice. Later, in couple years later, it will be lunar resource lander, and in between of them will be lunar resource orbiter. It also some remote sensing, including imaging. What is on the surface of the moon? No atmosphere. Temperature is great range. It is very difficult to work in this environment. It's temperature from 120 Kelvin to 410 Kelvin. And if very low temperature is, you can just put a lot of warm things on you. But where it is 410 Kelvin, it is something which you cannot withstand for a long time. Meteorite and micrometeorite bombardment, cosmic rays, and of course, you can see this is astronaut of Apollo 14 installed TV camera, and you see a little spherule about 1 millimeter across with micro craters on it. It is everything is bombarded. Here on Earth, we are protected from this by our atmosphere. Surface morphology of the moon. Highlands, what is look bright here, and dark, so-called Mare. It is, you know, we people, when we see something, we are based on our experience. And first we started to look, we people, in telescope, in the era when it was a lot of travels along the seas on Earth. So when in telescope, the people, astronomers have seen these bright things, they say, okay, it is terra, it is continents, and dark, it is mare, seas. Later, it became obvious it's not the case, so it is mare, filled, not water, but with basaltic lava. Surface morphology. Highlands, on the left you see highland, a lot of craters of different diameters. And mare, it is, mare fills basaltic lavas, fill different depressions. In this case, Mare Imbrium fills great crater. Types of lunar rocks. First of all, you see that what you see on the screen, they have different colors. Don't believe it. It is play of photography. All of them are boring gray with little tint, only little tint, a little reddish, a little bluish, but it is tint. It's no color. And they are in their composition, they are basalts or anorthosites or norites, troctolites, and in the continents, it's a mixture of all of these things. It's breccias and melted, remelted by impacts, impact melts. So, okay, lunar rocks, mineral composition. Plagioclases, they are high calcium, olivines and pyroxenes. Minerals with volatiles are absent or practically absent. Rocks, anorthosite, narite, tractolite, breccias, and impact melts in Highlands and basalts in Lunar Mare, no granites. This is so-called Genesis rock. It is anorthosite. You see how astronaut of Apollo 15 found this rock and makes its image. And on the left, this rock is in the laboratory in Houston. And here is breccia. You see, it is a mixture of very, very different things, brighter, darker, and so on. Again, this pinkish color of all this image, don't believe in it. It is gray. Then I show you it is Apollo landing, Apollo 16 landing site. It is a regional situation. Arrow shows place to which goes the lander. It is a lot of rough topography. Then you see closer that there is some plains, and these plains where spacecraft landed. And before this landing, these plains in the lunar highlands, they were thought to be highland basalts, highland volcanism. But this lander brought samples. They showed no, it is just fine fraction of ejecta, impact ejecta. And this is, you see, very good image, and you see lunar module of Apollo 16 landing site. You see even traces, footprints, how astronauts were working there. And this is in the morphology of the moon. Dominates crater, it is south pole of the moon above telescopic view. It is Apollo 16 landing sites below. Craters, craters, craters. Amount of craters per area provides a possibility to say what is age of this given place. Of course, for that it was necessary to bring samples and to compare age of basalts from different places with amount of craters counted in this area, and then we got some correlations. So now we can estimate age of different areas on the moon just counting craters. There are a lot of tricks there, but it is possible and works very successfully. This is global distribution of craters, larger than 20 kilometers in diameter. You see that a lot of them in so-called highlands, and what is in the middle of near side, it is where is Mare, it is much less larger craters. Morphology of lunar craters depends on their diameter. Smaller than 10 kilometers, ball-shaped. 15-20 kilometers, transition to central peaked. 20 to 90 kilometers, central peaked craters. Larger than 90 kilometers, it is so-called ring basins. Then Orientale basin is the youngest large impact basin on the moon. You see several rings, and you see that ejecta from this Orientale basin, they cover significant part of the moon surface, and it is only what can be possible to map, and very fine fractures, very fine percentage, it covers practically all the moon. So moon surface is superposition of ejecta of different craters. Secondary craters. You see on the lower left crater Copernicus, and you see chains of craters extending, radially extending. It is ejecta from Copernicus flying and striking the surface and forming so-called secondary craters. This is a problem when you want to count craters and say what is the age of this given place. It is a problem how to get out, to select out the secondary craters. Geochemical specifics. Observations. Practical absence of volatiles, water, carbon dioxide, deficit of moderately volatile compounds, deficit of potassium, of sodium, enrichment in refractories. What follows from this? It says that explosions, crater-forming explosions, were not volcanic. Craters are impact. And it was high temperature of the process and possibility to lose volatiles in global scale. It led to hypothesis of so-called giant impact. I will show what is this later. Observations, deficit of siderophiles. It is observed only for primary magmatic rocks. While highland breccias, impact melts, they enriched in siderophiles. Why? Because brought by meteorite impacts. But the fact that primary magmatic rocks has deficit of siderophiles, that siderophiles did sink to the core, but core is small. It is also supports hypothesis of giant impact. Regolith, what is on the surface? A few meters of mixture of very fine dust, sands, and larger pieces. You see on the left that it is astronaut footprint. So regolith behaves a little bit as something wet, because in vacuum there is no gas covers on the surface of particles, so very good cohesion. So it is absolutely dry, but it behaves a little bit like it is a little bit moist. On the upper right, you see it is something boring. It is our Luna 16 sample, black, very fine. Lunar volcanism. You see yellow arrows show lava flows. Lava flows are badly seen on the moon because lavas are mostly lavas in Mare. They were liquid, so flows were quite of low thickness, and they are reworked by regolith formation, by meteorite bombardment. So you can see them only where sun is very low, like in this case. And you see also, look here, yellow, it is like little rivers, Sinuous rivers, but it is channels made by flowing hot lava. And this is crater Alphonsus, and in this crater, Soviet astronomer Kozyrev could see some phenomena, gas escape. And now we see what was there. We see craters without rims and some black halo around. This is something like kind of piroclastic deposits. And it looks, it's impossible, it is very young. But later we will see that probably at least there is some evidence that volcanism on the moon, maybe some and very little scale, is still alive. And this is so-called Gruithuisen domes. Maybe it is not basaltic volcanism. Necessary to fly there and bring samples. And these are tectonic structure of tension, extension, compression, and like this is compression. It is Sinuous rilles. On the lower right, you see similar things is on Earth. It is Australia. And what is interesting, when we geologists studying the moon, we just see this sinuous ridges. So, okay, it is quiet tectonic compression. But when we returned to this event, historical event, Mare fault in Australia, it was very strong earthquake, and it's shake and formation of these features. So probably on the moon, there was also formation of these compressional features. It was accompanied by shocks, by mooncakes. And this is graben extension, and this is large impacts. They play some role even in distribution of tectonic features. You see, it is circular feature on the left. It is basin of Mare Imbrium impact, and radial in it is some graben. Geological history of the moon. Major stages of geological evolution were determined based on analysis of telescopic images. So we knew that time was the first, was the second, the third, and so. But the types of geological processes and the absolute dating of events became understandable only based on analysis of data acquired in space missions. So these are the moon, as we can see from Earth. Mare Imbrium, it is some Mare Nectaris, which basin of Nectaris, it is well not so good seen, it is old. Basin of Mare Imbrium, it looks more fresh. It is some crater, Eratosphene crater, superposed on what is in Mare Imbrium, and the youngest crater is Copernicus, and the youngest is, you see in the lower part, it is Tycho. So geological periods, pre-Nectarian, most ancient, Nectarian, Imbrian, Eratosphenian, Copernican, the youngest. Typical rocks, pre-Nectarian, Nectarian, significant part Imbrian is breccias, Highland breccias and impact melts. Imbrian, Eratosphenian is Mare basalts, and Copernican, rocks of craters. And now we know that there also may be something volcanic there. So absolute ages, Mare is 3 to 3.9, Highlands 3.9 and 4 to 4 and higher, and young craters 100 million years and smaller. Geological history, it is early intense bombardment, volcanism, which we first thought was over around 3 billion years ago. Probably not. And late bombardment coming to today. Structure of Lunar interior is an Anorthositic crust. It is some Mare basalt superposed on it. It is mantle and very small, rather small nucleus, core. And origin of the moon, hypothesis of giant impact. It is considered that in proto-Earth was shocked, impacted proto-Mars-sized body. You see on the lower right, then its significant part of ejected, and it was this ejected were very hot. They were losing volatiles and moderate volatile things, and then they gradually assembled in what we have now, the moon, in near Earth space. Our moon is satellite of Earth. But this is a hypothesis. Very good, very attractive hypothesis, but we don't know, is it true or not? What we know about the moon? Polar caps, volatiles in permanent shadow. What is their source? Of course, meteorites, when they struck the moon, many of them have some volatiles content. This is carbonaceous chondrites. These volatiles, water vapor and so on, they fly around, and in volatiles where in impact in deep craters, there is very, very cold. They are captured there, and we have volatiles there. But what I showed you in this Indian satellites, Chandrayaan-1, it showed that there is some on the surface of regolith particles, some very thin layer of water. This is reaction of sun, wind from the sun, protons from the sun. They struck the lunar surface minerals and formed this H2O. And this H2O is it can, when it is too hot, it can escape, and it can go to the poles too and provide some, and also some volcanic volatiles also exist in the moon. Now we know this. Question: up to which time lunar volcanism occurred? Another problem of non-basaltic volcanism. We need to bring more and more samples. Maybe something will provide us this Chan E5. Structure of lunar interiors, known badly. We don't know what was going on the moon during the first, not very well known. And origin of the moon, giant impact or accretion. This is what I was saying. This is upper 1-2 millimeters, varies during the lunar day, content of these very thin littles of something like water. This is new data on water of the moon. You see it is epithermal neutrons allow us, neutron spectrometer, to map this. But it's a lot of enigmas there, because some, you see, for example, to the right, you see 3 craters. Havors, it is Shoemaker and Faustini. And one of them in the middle has a lot of more hydrogen than two others. Why? We don't understand. Why is this difference? This was some attempt, successful attempt, to show that this is really water ice in the south, in the lunar poles. It is lunar L-cross experiment when some body was intruded, struggled into lunar surface in the area selected by the remote sensing, and it shows that several percent of water ice in this given place is present. And this is evidence of very young lunar volcanism. Or maybe it is extrusions of magmatic foam. This on the upper is so-called crater Ina, first discovered in the flights of Apollo 15, then 17. It is strange D-shaped crater with many strange hills on it. And these hills, they steep sloped, they have quite little amount of impact craters on them, so they look like young. But it sits, this inner crater, on top of large basaltic volcano, and which age is quite normal, like about 3 billion years. But this, if you count craters, just less than 100 years. Why it is? So Jim Head and his colleagues, they suggested it may be old extrusions, but not normal basalt, but basalt filled with many, many bubbles of gas. And these bubbles of gas, they made behavior of these extrusions very specific. First, they behave like, not like liquid, like viscose. They form steep slopes. And then when meteorites impact on them, they just form kind of like channels. So if you count craters on them, later craters, you will get bad estimate. You will get wrong estimate. But maybe it is correct, maybe not. So we will need to go to this place and get samples. And what on the lower side, on the lower, it is so-called ring-mouth volcanic dome structures. They are also show that they are very young, but if you will believe to hypothesis of Jim Head that if it is magmatic foam, then it may be old ones, maybe not. Necessary to go and bring samples. And this is new data on water of the moon in piroclastic deposits. It was found that with very strong, very new techniques, that they have amount of volatiles comparable with what is in terrestrial basalts in mid-oceanic basaltic extrusions. And this is water in piroclastic deposits. It shows that it is indeed, there is some water. But if there is water in lunar interiors, not everywhere, in some places, but it's a why we should play in this giant impact game. Maybe it was some different kind of formation of the moon, and my colleague in the institute, academician Galimov, he worked with his colleagues on different, it is just due to accretion, you may have obtained the moon and Earth with their characteristics. And thank you for your attention. This is me 1.5 hours ago. I went with our dog to breathe fresh air before my talk. Thank you.
Okay, Professor Basilevsky, thank you so much. Sasha, thank you so much for this very interesting talk. So in one of your very last slide, you mentioned that one important thing is to find out what happened, in the first 600 million years of the lunar history. How could we do that? By what kind of measurements or sample return can we solve this question?
You say
what's going on the moon during the first 600 million years, and by what way can we answer the question?
Say again, a question about which polar caps to which time lunar volcanism occurred?
What was going on the moon during the first 600 million years?
Because we know this not very good, because it was bombarded, and we know a lot of bombardment which happened up to 4 billion years ago, 3.9 billion ago, 4 billion ago, and what was before, it is covered, reworked by these younger impacts, younger basins. So the good way is to go to polar area, to South Pole area, and there is rim of South Pole basin, and it is huge basin. It is about several thousand kilometers across, and on this rim, I think, and not only me think, that gradual this thorough sampling, and there are some places where maybe not some big massifs, like big fragments, like 1 kilometer across, so 2 kilometers across fragments, and work with these big fragments, trying to understand. Chinese Chang'e 4, it landed inside this big South Pole Aitken basin, but it landed inside some smaller craters superposed on that one. So everything was already reworked, and it is landed on Mare-like lavas there. So it is good step too, but we should study the rim of South Pole Aitken basin.
Okay. Any questions from the audience? If you have questions, please unmute yourself and then ask the questions. And also tell us your name, so that we know. If no immediate question, I have another one. Shaka, you mentioned also that actually in this slide or something, the one nearby, that now that we know that there are water, high water content from the mantle, right? From the from the, what do you call it, the these tiny grains, and then you said that the composition. I think you meant the D to H ratio is similar to the ocean water of the Earth.
Okay, say again. I didn't get your question.
Is water, water, there's a high amount of water. I would say that not high amount, there's some amount of water found in the mantle material from the sample returned from Apollo 15 and 16.
Yeah. There is actually there is. It was in the samples brought by Lunas and Apollos much more material. We didn't see any water content. Now we start to see this because this very little, but nevertheless they are. We see them, and like here we see that even in lunar highlands there is something containing water. There is some craters in central peak of these craters. There is this land measurements show that central peak has higher content of hydrogen. It is central peak. It is something which is loses. It is negative balance. So it is central peak. It is something what was uplifted during the cratering process. So it says that there is some not very dry materials, not very dry rocks in lunar interiors. So we need to have more samples.
Okay. I'm just wondering whether the D to H ratio is it the same as the Earth's ocean waters? The isotope composition. Perhaps you don't know. So, any other questions?
I convinced everybody.
No, they're just thinking, to ask you tough questions. Now, everybody, if you have questions to Professor Basilevsky, but you don't want to ask him now, and you could write him, if you don't have his email address, then you could send it to me, and I will pass the.
Okay, good.
Right. Okay, great. Shasha, I thank you so much, and keep warm, and keep.
Okay.
Okay.
I will go out. I will go outdoors. You see, to what place?
Yeah.
Goodbye.
Thank you.